Hello again, and welcome to the third and final installment in the series of Test 2 masterclasses. So now it's the time for Learning Unit 4, which is on linear programming. So once again, I'm going to share my screen. With this question over here. This is one of my own questions, and I've just thought about it. I'm going to add a couple more dimensions to this so that we can kill as many birds, shame poor birdies, with one stone as possible. So what is linear programming all about? Where we have two or more limiting factors or constraints, and we need to find the optimal product mix, we would use this method. So the number of units of each of the products to make in order to bring in the greatest contribution. Whereas in Learning Unit 5, we answer the same problem, but we solve it differently when we have only one limiting factor. So that is Learning Unit 5, and the method is called contribution margin per limiting factor. But for now, let's deal with the linear programming aspect of it. So this company has two products, A and B. How many of each of them should they produce to make the most profit? So we need to design a linear programming model. And what does it contain? A few things. First of all, there's something called an objective function, which is either a profit maximizing criteria or a cost minimizing one. Yeah. Then we need to set up all of the constraints, and they must be in linear format because it's called linear programming. Then we will solve the model to find the optimal product mix. And lastly, we can then substitute those values into the objective function and determine the maximum contribution or profit for the business. So here's the information that we have. So let's look at part one. I'm wanting an equation that is going to maximize the profits. So what is the name of this equation? It's called the objective function. And the objective function is written in terms of Z is equal to whatever. How I'm going to do that is I need to have the contribution for each of the products, because this equation is going to be used at the end. Have a look at number 4. Calculate the maximum contribution using the values above. So when we have found the answer to number 3, we're going to take those numbers and substitute them into the answer for number 1, and that will give us the answer to number 4. Helps to know the plan of attack here. So in order to do the objective function, I need to know what the contribution is for product A and for product B. And that obviously is very simple. The difference between the selling price per unit for A of 400 Rand and its variable cost. So please don't forget here, this is very important. Otherwise, you're not going to know what on earth is going on with linear programming. Please don't forget, you must know the types of variable cost. If you can't do that, and you can't recognize or identify them from fixed cost and other irrelevant cost, then you're not going to be able to calculate contribution. And without that, you can't even start this whole linear programming thing. So if we have a look at it here, we're going to have something to do with labor hours, machine hours, and variable overheads. So what you must notice over here is these have Rand signs there. Because it's Rand signs, it indicates that these are all cost values, not quantities. These are costs. Just move that so it's visible there. So let us do a table, because you know how I love a table. It's very economical and saves a lot of time. We're going to have 2 columns for A and for B, and we're going to calculate the contribution. So that means that we are going to subtract your labor cost, your machine cost, and your variable overheads. So let's pop down and do that. Yeah. So notice here, I've just saved a little bit of time. There's the cost for labor, there's the cost for machining, and there's also your variable overheads. Take those numbers together, add them. For A, it's 200, and for product B, it's 90. That's very easy. I'll leave you to do that. Subtract it from your selling price per unit, gives me contribution per unit of A of 200 Rand and B 160 Rand a unit. So now to answer that question, I must write my equation, which I called the objective function. Z is equal to, notice what we do here. We put the contribution margin next to each of the products. So that tells me it's 200 Rand contribution for a unit of A and 160 Rand contribution for a single B. Now, let's then move on. We've done number 1. Let's try number 2. We want the constraints. I've only said labor hours and machine hours, but we're going to add in a couple of others. So when it comes to the constraints, I'm just going to type something up here for you. There, the top, we want a complete set of constraints. And what are the constraints going to be for? Let's include all of them. So the first one is the obvious one. It's for your inputs. Then there could be another one for annual demand. There's always what we call the non-negativity constraints. And there could be others. Maybe if there's a minimum special order. So depending on what the question has, you will either include a constraint for it or not. Right. So we are going to have, obviously, for the 2 constraints, which are for labor hours and machine hours. So let's read the question and unpack it, see what is sitting in there for us. It says the total machine hours, 14,000 per week. And it also says, let's do a different color, total labor hours per week, 10,000. So those are the inputs. Those are constraints. But I'm also going to include some other information here. We're going to do an annual demand. So I'm just going to type that in a convenient spot somewhere. Here, we're going to say the annual demand for the products. We're just going to say for A, the annual demand is 600 units. And we're going to say for product B, annual demand is 1,500. So that means that based on its estimations, the business does not expect to sell more than 600 units of product A and not any more than 1,500 units of B. So let's get on then and let us do the constraints. So we're going to start first of all with the labor hours. First one. And now we are limited to 10,000 labor hours a week. So what we cannot do is use any more than those 10,000 hours. So we can use up to including 10,000. So how we are going to write that up is using the less than or equal to sign. So we can use anything like 2,000, 100, 7,000, up to 10,000, but no more than 10,000. And what we need here for the constraints is we need the amount of the input. We do not need the cost like we did when we worked out contribution. We need the amount of the input used in the production of 1 unit of each of the products. So we're going to need hours. So let's go and see if we can find any information. So here it says product A uses 6 hours a unit and B 5. So how am I going to write that up? Here we go. This one for the labor hours constraint, 6A plus 5B less than or equal to the 10,000 hours. So 6 hours to make a unit of A and 5 hours to make a unit of B. That's how we write up the labor hours constraint. Now let's come along and do machine hours. So what do I need again? Hours, not cost, but hours. So let's have a look at the question. Slightly different. It says the machine hours are 14,000 max per week. And it says the hours are allocated to each product at a cost of 5 Rand per hour. Now we seem to be stuck because for labor, it gave us hours. Here, it's not. So what we now have to find a way around is this. We needing to find the machine hours for each of the products. And we have some information. If we go up here and we have a look, to change the color, that 90 and that 20, that's the cost of machine hours. Now we know that it's 5 Rand an hour. So if we want hours, what are we going to do? Think about it. We know that to make an A, the cost for machine hours was 90 Rand. And if it's 5 Rand an hour, surely we can find hours. We divide 90 by 5. And what would we do for B? The cost in money terms for machine hours was 20 Rand. At 5 Rand an hour, obviously 4 hours. So let's work that out. Here is the workings. I need hours. So 90 Rand divided by 5 is 18 hours. So there we go. We put the 18 in front of the A. For B, it's 4 hours. We pop that in front of the B. And then the maximum number of machine hours available was the 14,000. Now I'm going to add in all of the other constraints. Remember I said we've got annual demand. So what we're going to do here is we're going to say, let's make it a bit bigger. The maximum demand for A, I said, was 600. So we cannot sell more than the maximum demand. So we're going to say A less than or equal to, and I can't type that sign up here on my keypad, 600. And we're also going to say B less than or equal to, what did I say? 1,500. And I'm just going to have to try and use this. And I can't get close enough to it. No, won't let me. There and there. So less than or equal to, please. I'm just not able to do that particular symbol here. Then what about the non-negativity? So if we are going to be maximizing profit, it surely is common sense that we need to make both of the products. So then in a mathematical sense, how do we say we must make product A and we must make product B? We need to have them. So they need to have positive values. So the non-negativity, it's too big. The non-negativity constraints. Oh, what did we do there? Sorry. That's even worse. Sorry, we're getting there. I'm just getting a bit tired. The non-negativity constraints, what are they going to be? That A must have a positive value. In other words, A must be greater than 0. Also, the same with B. B must be positive number, greater than 0. There's no other conditions here about any minimum order for any one of the products. So we are done then in terms of the constraints. So let's see where we are. We've done number 2. Now it says, using the constraints, solve for A and B. So we now need to find how many units of A and B will maximize the profit for this business. So what we're going to do is we're going to go back to our 2 constraints functions here, the one for labor and the one for machine hours. And we are going to rewrite them in the format of a straight line. So think of A maybe as X and B as Y. So all we're going to do is use basic algebra. So I'm going to start over here with what I had for my labor hours constraint. And I'm going to rewrite it rather in terms of B. I could choose A, doesn't matter. But if I choose B on the left-hand side, I must also go with B on the right-hand side. Or alternatively, A and A. The only thing you can't do is one of each. So all I'm going to do now is I'm going to isolate B, the 5 B's on the left-hand side. So that means I've got to take those A's and move it to the other side. So minus 6A. Then I want to rather write it in terms of 1B. So I divide every term. Remember, I must be consistent. Divide throughout by 5. And that will give me B less than or equal to 2,000 less 1,2A. Now I'm going to do the same with the constraint for the machine hours. So I'm wanting to isolate B on the left-hand side. So I need to subtract the 18A from the right-hand side, divide throughout by 4, and that's going to give me 2 inequalities written in terms of B. So what I can now do is set those equal to each other. So I'm going to take this over there, and I'm going to take that, and I'm going to set them equal to each other like I did here. Now, once again, it's just basic algebra. I'm going to group like terms together. So I need to have the A's all on the one side, the numbers on the other side. Be careful as to whether they have positive values or negative values. So to the negative 1.2A, I'm going to add 4.5A. Why? Because to move something to the other side, you subtract it or change the sign. And because it was a negative. So a negative 1.2 plus a positive 4.5 gives me 3,3 positive A. Now, what do I need to do? I need to just go and sort the numbers out. So I need to move the 2,000 to that side. So 3,500 less 2 gives me 1,500. Now what I'm going to do is divide both sides by 3,3 and round up to a whole number. And that will give me A is equal to 455. Now we need to find the value of B. So this is going to tell us how many units of B will bring in the most profit. So I have a choice. I can either go to this one or this one. Just have a quick look at it, pick whichever looks the easiest, but you'll get the same answer. And substitute our value of 455 for A into either of those. Right, so I've picked the one on the right-hand side. So 3,500 minus 4.5. I've substituted value for A into there. And I then found that B equals 1,452. So what does that mean? If this business produces 455 units of product A and 1,452 units of product B, that will then generate the maximum amount of profit. So that is number 3. And let's just check those values, because remember up at the top here, see over here, I gave an annual demand. So is the value of our A less than 600? And is the value for our number of B less than 1,500? So A, yep, is 455. It's less than 600, so that's good. And B is less than 1.5. If you should find that those values exceed the annual demand, something's gone wrong. Right, let's now get into the last one, number 4. Calculate the maximum contribution using these values. So our first question that we did, number 1, we came up with the equation that is going to maximize the profit. So that Z is equal to that objective function. All we're going to do now is going to substitute those values of A and B into that, and that will give us the maximum contribution. So just a reminder there on what that was here. 200 is the contribution for A. All I'm going to do is substitute the number of A's. 160 Rand is the contribution for a B. I'm going to substitute the value of B that I just found, multiply and add, and it will give me the value for Z. And that will give us the maximum contribution. So if we do that, we get 323,320. What I also want to do now is include a 5th part of the question, because something else that we look at in linear programming is called shadow pricing. What this means is, what effect does a change in the availability of one of the inputs have on your optimal product mix and also on the contribution? So what I'm going to do here is I'm going to type in a 5th part. Let's get it a reasonable size. And just bear with me while I type. I'm going to say solve the objective function if 1,000 more not labor, so I'm just looking down at my notes, machine hours were made available per week. So there is a new question. Solve the objective function if 1,000 more machine hours were made available per week. And we're also going to have a different final bit, I'm going to say indicate the change. Oh, dear me. In the contribution. There. So that's a whole different question. Basically, what this is doing is shadow pricing in practice. So only thing that's changing is the number of machine hours. So nothing's happening with the labor hours. It's still 10,000. So that constraint, we don't need to touch that again. But the one for machine hours, we need to redo that because it's not going to be less than or equal to 14,000 anymore. Why not? Because we have an additional 1,000. So let's see if I can actually type some of the answer in here. So what are we then going to do? Right. We're going to redo the machine hours constraint. And that's going to be the 18A plus the 4B. Remember, I can't do the less than or equal to, so apologies for that. It was 14,000. If there's 1,000 more, it's now going to be 15,000. And remember, it must be less than or equal to. So what I'm now going to do is I'm going to rewrite it like I did before. I'm going to say 4B less than or equal to the 15,000, and we're going to minus the 18A, and then divide everything by 4. So B less than or equal to, just remember, less than or equal to 3,750 minus the 4,5A. So what I've done is my new machine hours constraint. Let's see what it was before. It was 18A plus 4B less than or equal to 14,000, which when we wrote it was B less than or equal to 3,500 minus 4.5A. What have we got now? That's our new constraint. So what's the next step? The labor hours remains the same. So I'm going to do just like I did here in part number 3. I'm going to use the same inequality on the left-hand side, but I'm going to use the new one on the right-hand side. So I'm going to equate those two with each other. And let's just type that over here. It's going to be 2,000 minus 1.2a. I'm going to set that equal to the 3,750 that we just found minus the 4.5a. Then, just to not make myself look so stupid with the typing and to save time, I'm going to rearrange and I'm going to simplify, and I'm going to find for A, and we're going to come up with A is equal to 531. Now, next step, just repetition. I'm going to solve again to find the number of B's. So let's do that. We're going to say B is equal to the 3,750 minus the 4.5, and I'm going to put in the value of A in the bracket, which is 531. And if I simplify, I'm going to land up with B is equal to 1,360 units. So let's see what I've done. My new question So the question's at the top. Solve the objective function if 1,000 more machine hours were made available per week. So we're now going to say that the business needs to produce 531 units of product A together with 1,360 units of B, and that will maximize the contribution. So the last part, indicate the change in the contribution. So let's work out the new contribution, shall we? I'll just change the pen color. So we're going to do the new contribution. And what am I going to do? I'm going to use the objective function. I'm going to say Z is equal to, and we're going to use the same contribution per unit of an A, which is 200. And I'm going to substitute in the value of A, which is now 531. And then I'm going to add, what was the contribution of B? 160. And I'm going to times that by the new quantity of 1360. Close the bracket. And then we're going to say Z is equal to, and it must be money, 3,223, 800. So that's my new contribution. Let's see what our initial contribution was. And we can find that over here, 323, 320. It's a little bit out of space. So now what's the last part? Indicate the change in the contribution. So we see here that the contribution has increased because of the greater availability of machine hours. We were able to make a different optimal product mix that resulted in the generation of more profit. So what we must now do is clearly state what our answer was. In other words, we are going to say that importantly, the increase in the contribution is equal to the difference between them, and that is equal to 480. So that, everybody, is shadow pricing in action. So it's shown us the change in the profit of the business as a result of a relaxation of the availability of one of the inputs. And that, everybody, is it from me. So we've done very comprehensively Learning Unit 3, and I've taken this simple question on linear programming and I've adapted it to account for as many possible combinations of questions that you might reasonably expect in the test. Okay, so for now, it's goodbye from me. Best of luck, everybody, for the test. And we shall meet again when it is the time for the exam.